For this project, I chose to do a pendulum model, and this is using a nonlinear drag. So drag is proportional to velocity squared in this case, and that adds a layer of complexity where you can't solve it algebraically and actually need to use a numerical method. So the main differential equation here is that angular acceleration, so that's the second derivative of theta, the angle, will always be equal to negative the force of gravity divided by the length of the pendulum times sine of the angle theta. And with this model, you add in the second term, which is subtracting out the acceleration caused by drag, so air resistance, and that's what's being computed in columns J and K. So what that means is that if you look at this graph here of the position of the pendulum over time, you'll actually see that motion decay, and eventually it should come very close to stopping. And that's actually one of the, if you look over on the left in this column, these are all terms you can manipulate to change the starting conditions. So you can see that if we were to say double the air resistance, you'd see a much faster decline in angular velocity, and the pendulum motions would shrink much quicker. And then if you were to increase mass, that increases the amount of kinetic energy the pendulum has, so it decreases the effect of the same amount of air resistance. Making that much lower, you'd see it would have a much more significant effect on the pendulum. That's very consistent with what you'd expect from how physics in this world operates, which is encouraging for the accuracy of the model. Although it is something to note that if you set the air resistance term to be equal to 0, you see this increase in the momentum of the pendulum, which really should not be happening, but that's because of the inaccuracy with the numerical integration method. So I did switch to doing the second order Runge-Kutta in order to improve that, and it did decrease the rate at which that happened, but it is still occurring, which kind of calls into doubt the accuracy of the other predictions here. But other than that, it does align with reality, although this model allows you to put in any value for the starting angle, including things that are far greater than the actual number of radians in a circle, and that can generate some pretty crazy looking graphs like this one that are caused essentially by a pendulum starting with